All right, thank you so much. So, Technology is a public consulting firm, and our core is, and this project came out of a frustration that for a few years now it is novelty for the scientific and originality, but at the same time, how we do a bad job in measuring it or having indicators that help us understand how novel new is or new presentations are. This is what this project is all about, is trying to contribute to ways of measuring the originality of ideas in a better way. That doesn't mean that all originality is good. It's more about measuring how we can measuring how we can see how researchers are taking risks, are trying new things. We have many other metrics to see how is the quality of the research or quality of different outputs. So here is really about trying to understand how to measure novelty more effectively. I propose a new concept, is this novelty vector that I'll show you. This is all based on machine learning tools. Project was about is trying to test the hypothesis that this novelty vector is a good way to measure, to understand novelty. What's new about this? So I developed this novelty vector that is based on the text of new ideas and of art. I use a new type of data. I use data from the full text of scientific proposals sent to a funding agency, one of our clients. That has both successful and successful proposals and has all the scores from experts according to the quality of the proposals, the novelty of the proposals, and some other characteristics. So this is the data that then I use to confirm or to test how this novelty vector can predict the review scores that we get from the assessment of these scientific proposals. I developed an algorithm that combines genetic machine learning with random forests, basically to show or to test whether this novelty vector can learn about the scientific reviews, about the novelty scores of the proposals. And what I see is that these novelty scores, or the features from the novelty scores, learned very fast. And novelty scores from the reviewers very well and very fast. But only for novelty. It doesn't work well with other things. So it's something that is really specific to novelty. I'm capturing something that is really looking into the essence of what is new, what's original. Beyond that, I try to more than just a pure correlation, a pure prediction, and put these indicators into an econometric model that tries to predict or assess the value, predict the review scores, taking into account other factors such as the quality of the proposal, the quality of the team, and some other characteristics here, the field. And after accounting for all these things, I see that the novelty vector is still an important predictor. So after controlling for all these other characteristics. Then using text from proposals and abstracts that have been known to lead to a Nobel Prize, and it also works with publications, so not only with proposal text. The characteristics from this novelty vector, again, following the same methodology, the same econometric methodology, they are relevant, important, statistical significant to explain how a paper is then associated with a Nobel Prize. So that's more or less what all of this project is about. The general steps are about computing this novelty vector. I'll show you. Is a bit technical, but I'll explain the essence of what it is. Then this novelty vector is literally a list of numbers. So we try to extract, to reduce the dimensionality of this vector and try to get some more tangible indicators. These go through the machine learning process that I showed you with this genetic machine learning model. And what I see is that the novelty vector predicts the expert review scores with a 96% precision. But doesn't predict anything else. So it does a very bad job trying to predict the thing, doesn't really learn about anything else. So it's really specific about novelty, which is a good, is a robustness test. If they would be able to predict everything, then it would be something to worry or to be not so sure about. So as I told you, then I also put in a different framework that controls for the quality of the proposal, year, and other metrics, and these elements of the novelty vector are still an important predictor. But again, not to the other characteristics. It doesn't predict the funding decision after accounting for all of these other indicators, and doesn't predict also other characteristics of those proposals. And it is an important predictor for Nobel-winning articles. So where are we on measuring novelty? In economics of science, there has been a lot of work using references of articles, whether new combinations of journals being cited or uncommon combinations of works being cited, a proxy for the novelty of that work. There has been a lot of criticism about that because journals are not the best representation of the knowledge space. There are many reasons why new journals are created that then influence the existence of a new pair combination. Sometimes it's a strategic choice from publishers. So these are becoming less prominent, and the literature is going more to explore the text. There are papers measuring when new words appear, but again, not new words. New words are not necessarily novel. Sometimes there can be just word variations. There are a lot of issues around these indicators, and the same thing with new word combinations. Not all combinations are novel. Some combinations can be more novel than others. There are problems with synonyms or spelling variations. So there's a lot of criticism with these past metrics, and we are now moving more towards using embeddings. This is a mathematical representation of text that goes beyond synonyms or the spelling, really captures the meaning of text. So there are two publications that are using word embeddings. And I'll show you more or less, give you an idea what they do. But before that, just an overall, these embeddings are, they translate words or text into these mathematical representations that measure the extent to which different features of text are there, if some words are there or not. So it doesn't really matter the exact usage of the word because it's going to be taken into account that word, what comes after the word, and tries to understand the topic or the general meaning of that text. And I'll give you another example very soon. So on the past projects that have used these types of vectors, they look at imagine you have a focal article, a publication. They create the embeddings of this article, and then they compare the embeddings with the references, or the art, of a focal design distance between article and the what I show in this project, this doesn't work so well. This is something that works very well to see if they are related, if they are addressing the same topic, but the distance between these embeddings is not really saying much about novelty. So I take a different approach by creating this novelty vector, which takes this idea. The concept of embeddings was shown first with this paper from Google, where they get text related with topic of king. They get the embeddings from this text with the topic of man, the embeddings and of woman. And when they do this simple operation with those vectors, they see that the resulting vector, when you subtract man to king and add woman, you get to a vector that is very close to the vector of queen. So this was the way that they first shown that these embeddings can carry meaning, and you can learn, they see through word variations and so on, and get the meaning of text. So the hypothesis for testing on my project is that if we have the embedding scientific contribution, and we have also a of what is prior art, the knowledge should actually be the subtraction, is what is new, what is left about an idea or an existing publication should be captured by the resulting vector that comes out of these operation. And that's what then this novelty vector is all about, is testing how this resulting vector can predict the scientific review scores from the experts. So the data sources that I used are these full text proposals. I have successful and successful. Then the evaluation according to different categories, including the originality of each of them. And for all of these proposals, I linked them with their references, linked with OpenAlex, all the titles and abstracts that are on their references, and then boost a little bit with publications that are similar to the references, but published before the date of the proposal. So has a expanded reference list that is considered the prior art for each of these proposals. Then we have scores for the feasibility, the CV, the quality of the CV, the quality of the proposal, and then the degree of originality. That's what I'll be using to test the indicator. They are ranking from 1 to 5. And here in this test, what I'm doing, I'm trying to predict highly novel ones. So I'm just trying to make a classification, trying to see if the novelty vector can predict whether the proposals rank on the top originality according to these review scores. Stage, that's what you're trying to predict. And the reviewers are asked to have this 1 to 5, and they are asked not to compare publications within the cohort of publications that they are assessing. They're asked to review according to what they think is in the current state of the art, whether they think it's the 5% most original work that they have seen. So it's not something that is compared with the cohort of proposals, is what the experts think are the most original in the world. So that's what I'm predicting, a dummy variable or a binary variable that is equal to 1 if both reviewers gave a 5 to the proposal. This is just a summary of what's done. The raw data is the review scores, proposal text. Then I have the references from which I get prior art, titles and abstracts from the references boosted with related work with this. I did the embeddings of the proposal, the art, I average proposal, so this is proposal level, and I get a multivector for each proposal by making this operation. And this is what I used. There are many ways to create vector embeddings. I use this now little old one I'm updating with Cybert. And the hypothesis for testing is whether I can predict these novelty vectors. Now, I'm not going to go through all of these, but the idea is that this is a vector of over 700 dimensions, and I'm just reducing the dimensionality, trying to get things that make some sense instead of feeding all of the 700 features of the vector to predict. I'm trying to create some indicators out of these vectors that can help us understand a little bit, open the black box. If I would use directly the indicators from the vector, which I did, it results in even stronger prediction, but then is a complete or will be a complete black box. So these indicators go through a genetic machine learning algorithm that consists of when you have a very large number of possible variables or features, it goes through an iteration that is inspired by natural selection to see what are the combinations of variables that matter the most. So it's just a process that go generation after generation, combining the features that matter the most and dropping the ones that don't matter as much, to find a final set that should be a better performing one. And when I first used this, when I first saw this, I felt it was a little bit of a meta science, but beware that it's something that also NASA uses to find the right angles and the right designs for their antennas to find the most well-performing ones. And is something that in the end works very well. So the idea is I have a training data and a testing data. The testing data is that the model the learning model never sees the testing data, so it's only working on this training data. It's generation after generation testing different combinations of features of the novelty vector and keeping the ones that matter most. And then in the end, tests the ones that perform the best on this training set, test the performance on the training set, test the performance on the testing that was never seen in the model. And the results, this is the after each generation, just getting better and better at the performance of the prediction for the scores, and we get this 96% precision for the best among these generations when I use it on the test data that was never seen by the model. Of this algorithm is would this work regardless on anything? That's when then I pursued the exact same methodology, trying to learn using the same novelty vector features, trying to learn about predictive funding decision, predicting other variables from the review. Is that it works very badly. It doesn't learn. It's not something that cannot really explain anything. Is really good to understand novelty, but even though the scores of the reviewers are correlated with the funding decision and the feasibility score, they do not work here. So it's really something that can be used to predict novelty, to flag when we find a possible highly novel original work, but is not predicting everything under the sun. And the econometric model, again, I'm predicting these high novelty scores, and I use reduce the indicators, trying to capture all the variability of the novelty score in something that can we can feed into a logistic regression. And here the idea is whether the variation that comes from the novelty vector is still important after we take into account the proposal quality and the CV of the researchers. So it's not to see if it's something that is just picking up on other variables, or if it's something that still matters after controlling for these other important characteristics, and also the field and the institutions of the applicants. And what we see in this test is that yes, these indicators still matter after taking endlessly comparing things that have similar quality and similar for all the other characteristics. And when I try to predict other things, so the funding decision, these features do not matter anymore. Final element of the project is the external validity, other types of data. So here using publications data instead of proposals data. So I take a data set that is of articles that have led to Nobel Prizes. So this is not the articles, all the articles of Nobel Prize winning, Nobel laureates, is really the articles in their early career that led later in life to their Nobel Prizes. And is from this data from Lee and al. And these papers that received these Nobel Prizes are expected, or we do believe that they have highly novel levels of novelty. However, they are also very high quality. And if we only use Nobel whether or not they got the Nobel Prize, we have the element of quality that we need to be able to distinguish. So what I'm trying to test is if the novelty vector or novelty indicators are associated with the probability of receiving a Nobel Prize after accounting to the quality, for the quality, or proxies of the quality of these Nobel Prizes. So to do that, I have a control group of papers that were published at the same time and comparable quality in terms of proxies. That is in the same journal as a ex ante pre-filter of similar quality, similar topic, and then I account to the number of forward citations, how many times they are cited in the future. So this is the new type of data. Nobel Prize, I have 10 papers that I compare each Nobel Prize paper with 10 papers that are the most semantically similar, because also in the same journal we can have multidisciplinary journals. So within the same journal, I take the 10 that are published that have the highest semantic similarity to each Nobel Prize paper. All of them will have their references, their prior art, and then I create the embeddings for all of these to pursue exactly the same strategy. And what I show is after accounting, so controlling for for being in the same journal, same topic, and after accounting for the forward citations of these papers as a proxy for quality, the novelty vector or the variables from the novelty vector still matter and are important predictors of being associated with a Nobel Prize. So wrap up, develop a new method or new concept for this scientific novelty that is a very good student when learning from expert review scores. Is statistically significant after accounting for other factors, so it's not the pure correlation that is picking up other things, so the quality, CV, strength, year, and field. So it's really specific to measure novelty. It also works in a different data set, so not only in proposals data, also in other types of data. Now, this is a new tool to measure novelty that maybe can be used in other areas too. Patents, startups, coding, artistic creations. With patents is something that we are trying now. But here we are learning from these expert review scores. Is there any other better way to do this? We think this is a good way, instead of just assuming, okay, combinations of journals, this is what we think should be novel or not. Here we are really trying to learn from something that real experts looked and gave their opinion. But we'll always have a trade-off here between performance and interpretability. Right now, we try to have this list of indicators that can help us understand if what features matter the most or less, but still it will only give you results like this, where you can have all the features and see which ones can matter the most or not, but it's still something that is harder to interpret. So the way how we are using it now is giving to some of our clients a portfolio view within what they are funding. What is the percentage of the works that are, according to this indicator, highly novel? Is this according to what they want in terms of fostering risk-taking, in terms of fostering originality? At that level, at that portfolio view, things can work very well, but then to understand each of the features that are underlying this indicator, that element is more difficult to interpret. Thank you very much.
Thank you very much.
Cool. Okay, hi everyone, thanks to the lightning talk. As I said, I thought this is only 10 minutes, so hopefully I will not run over time too much. So I'm here to talk about how one of our customers, so I'm with the Institution of Engineering and Technology, we're the largest engineering learner society in Europe. We've got 160,000 members, we publish books, we publish journals, we publish the Inspect database. We also organize events, and we have our own TV crew as well who are here recording this. So I'm here to talk about how one of our customers is using Inspect Analytics, an analytics layer built on top of the Inspect database, to be able to generate a cohort of more employable engineering graduates to take advantage of the CHIPS Act. Now, many people here will not be familiar with the CHIPS Act. There have been some seismic changes in global research and production, the supply chain problems after COVID, I remember I was trying to buy some new headlights for my car, and they were going to cost £2,000 for a headlight for the car because you couldn't get the microchips. The factories closed down in China. Anything electronic was just, the price was through the roof. And the US brought in a new law in August 2022 called the CHIPS Act, which tried to do what's called reshoring, bringing back semiconductor fabrication from overseas, from Taiwan, India, and China, back to the US, so they weren't so reliant on things being made elsewhere and shipped across the world. There's a lot of money there as well, $280 billion to enhance semiconductor fabrication. And of course, all research universities are trying to work out to get some of that money, right? $13 billion for research and workforce training, and US universities can significantly benefit from working out how to get some of this money. A lot of it is going to corporations as well. So here's an example from the Wall Street Journal, how there's a company in the US called Micron Technologies who are spending $100 billion because of various tax incentives they get to be able to set up a new fabrication plant, the big buildings with thousands of employees wearing the white full body costumes and everything in clean rooms, to make semiconductors. They're called fab plants. The problem is, other companies in the US that have done this have found that they've built these plants, they've set them all up, they're all ready to go, and then they don't have anyone who can work in them. They don't have the skill sets. Engineering graduates in the US just don't do that stuff. So they have to fly in dozens or hundreds of people from Taiwan, from overseas, to train the local workforce, which delays everything, costs them lots of money. So, just to jump back to InSpec, the database we make, we bring in content from hundreds of publishers, from hundreds of journals. We index it and we say these articles are about these specific topics. So we have a thesaurus we've developed since the 1960s, updated every year. And it's very niche, very fine-grained, very granular. So it's built for people to be able to find research articles on specific topics. We have 10,000 terms in the thesaurus. And then this is what an InSpec item looks like. It's probably too small to see on the screen, but we've got the bibliographic data, we've got the abstract, we've got the control terms, the thesaurus terms that we add. And then we have subject classifications and numeric data and things and references and citations. This is used by hundreds of institutions worldwide, including Syracuse University. And what we've built over the last few years is InSpec Analytics, which takes the information from the abstracts. So for example, this item, the authors is from Syracuse University, so we build a page for Syracuse University, and a page for the 36,000 institutions in there. We take the citations and we add that to the citation count, the article count, etc. And then we take the thesaurus terms, we say, this institution has published hundreds of articles on this particular topic. And then you can see how many times they're cited, and you can see which authors they are, etc. We say they've collaborated with these other organizations on these particular topics. That's how many times those collaborations are cited. That's a tool that InSpec subscribers get. And what we realized was, because we can see what Syracuse University does. Now, they are very, very good research university. They've got over 300 articles in the last 10 years on learning artificial intelligence. This stuff here, this is particle physics. They're involved in Higgs boson, the CERN project. They're doing stuff on gravitational waves. They're very highly cited for this research. They're doing stuff on the internet and black holes and biomechanics, and none of that is really much use to train your graduates on how to work in a semiconductor fabrication plant, right? You can be the best organization in the world at black holes and gravitational waves, but you need people to be able to make chips, right? So, luckily, Micron Tech also publishes research, right? They're a corporation, they're not publishing as much research. And you can see here what Micron Tech is doing. The green bars here are what Micron Tech is publishing research on. So DRAM chips, NAND circuits, solders, copper, silicon, storage management. That's what Micron Tech is talking about. That's what Micron Tech needs people to be able to do to come work for them, okay? So here you can see the green bars here are the number of articles that Micron Tech is publishing research on, compared to the purple bars, which, by the way, this scale is logarithmic, okay, on the left. The purple bars is how many articles Syracuse is doing. So immediately you can see these are areas where Syracuse needs to modify its syllabus to be able to do more work, for example, on silicon, failure analysis. They've got no research at all on solders. So Syracuse wants to then be able to modify its engineering syllabus, and they have significantly increased their budget because there's a lot of money floating around to be able to do the research and development. They just don't know exactly what subjects to do. So being able to say, well, we need to concentrate on solders, we need to concentrate on ball grid arrays and chemical mechanical polishing, which they don't do any of at all. This allows them to define how they need to modify their syllabus. You can compare organizations and see that Syracuse is doing a little bit of work on semiconductor doping, no work at all on metallization, which Microntech is doing. Microntech is doing a lot, the blue bar there, on lithography, which is actually printing the chips. And Syracuse is doing almost nothing. So they can identify what work they need to do. And then, since we did this, so we went in, we gave training courses to the engineering faculty. They can identify, and there will be a bigger talk this afternoon going into details on how they did this. But here you can see this, the light blue bars is what they've done since, or in fact, what they've done in the same time period, with extending out the time period to 2024. So now, since they have started using in-spec analytics to be able to identify areas they need to concentrate on, people they need to collaborate with, universities they need to collaborate with, people they could hire, new courses to train those engineering graduates. They've now significantly increased their research on analysis, on failure analysis, on silicon, on storage management. So just in the period of 1 year, they've gone from publishing almost nothing on storage management to 4 more articles. They've increased the research on FEA from 23 to 31 just in the space of 1 year. And on silicon compounds, they published 1 more article. But this is when they've been using in-spec analytics to be able to define what areas do we need to do more work on, who do you work with, and how do we provide a better cohort of engineers. So just to summarize, and I think I'm on time. So Syracuse University is using in-spec analytics to understand the subject gaps in what they're currently teaching undergraduates, to be able to prioritize which areas they need to do first, to be able to find out who to collaborate with, which organizations they can partner with to be able to do those areas which they have no background skills in, right? But they can collaborate with other organizations to do that work. And find authors to work with or to potentially recruit. And then also to be able to monitor the output to see if this plan is actually working. And as of when I looked yesterday, they have now started doing collaborative research with Microntech, which they've never done before. So now they're actually able to successfully collaborate with this massive organization, move into town, and start generating a cohort of engineers who are much more employable. So that's all. Thank you very much. Thank you.
Thank you. So everyone, I am Angelo Salatino, Research Fellow at the Open University, and I have to give here a little bit of a disclaimer. I've done this work in collaboration with my colleagues at the Open University and also some other colleagues at the University of Cagliari in Italy. And also I presented this work last year at STI in Leiden. So the title of this talk is diversity of expertise correlated to scientific impact? An AI-based large-scale analysis in the field of computer science suggests so. It's an unusual long title, but at least it gives away what is the promise of this talk. So understanding how to compose a research team, I believe it's really important because that can lead to the success of a research project, as well as to a better impact of our research papers, and more in general to science policies, and as well as best practices in order to push forward innovation. And diversity is one of the characteristics that has been studied a lot in order when it matters to understanding team characteristics. And indeed, different ideas, different perspectives, and different methods can improve the quality of scientific work. And also diversity can reduce biases, errors, avoid gaps, therefore improving the impact. If we look at the literature, diversity, as I mentioned, has been quite widely studied across several dimensions: nationality, ethnicity, institution, gender diversity, academic age. I mean, this means junior versus senior staff, discipline background, and team size. And what they all agree is that at least diversity leads to an increase of productivity, which is translated in terms of more papers, as well as more impact, which is translated with more citations. And also, this this team led from Al-Shebli in 2018 studied also whether different characteristics of diversity, among all these different characteristics of diversity, which one was the one that could lead better to improved number of citations. And ethnicity played a huge role there with an increased impact. However, what we realized is that no work was focusing on the relationship between diversity of expertise and impact. Therefore, we started asking, okay, can diversity of expertise within a research team influence their scientific impact? And this translates into, can diversity of expertise within a research team influence the number of citations gathered in the first 5 years? So, given this question in mind, I want to give you a bit of a glimpse of what is the approach in order to get there. So given a random paper from a dataset, we know who are the authors of these papers, therefore characterize the team, right? We know which year it has been published, 2015. We know the number of citations that this paper has gathered up to in the following 5 years. And what we can do is, if we extract the authors, we can look into the past of each individual author, extract the publication in the previous 5 years, and what we can extract is also a footprint of their research topics. So we can understand their expertise, where they are expert the most. And then if we are able, in a way, to understand how all these authors are different in terms of expertise, we can come up with an index that say, okay, this is the level of expertise, and see how the number of citations correlates to this expertise index that we just mentioned. So in order to get there, we need these 5 steps. First of all, we need to identify the data source, data selection. We need to assess the author expertise. Once we know the author expertise, we need to assess the extent of diversity within each team. And then we need to investigate what is the relationship between this team, so the diversity of expertise, and the citation that the paper has been gathering in the following 5 years. So as a data source, we use the AIDA knowledge graph. Now, the AIDA knowledge graph is a bit of a complex initiative because it integrates data from a lot of data sources, the OpenAlex, Imprimis. Then we integrate data from the DBLP for ingesting conference data. Then we include patent from Dimensions. Then we also include the computer science ontology for characterizing papers according to their topics, and other data sources. But here in this particular exercise, I'm going to focus on only papers that have been annotated with research topics. I'm going to discard all other data sources. What we did was, we have 25 million papers. In this particular exercise, we have 25 million papers in computer science that have been annotated with the computer science ontology. And to do so, we employed the CSO classifier. This is the bit of AI, so maybe I'm going to spend a bit more time just to give a bit more focus on this. What we do is that, given the papers in OpenAlex, we take title and abstract, we feed it to this tool, and this tool is able to extract topics that belong to this computer science ontology. The computer science ontology is the largest and a fine-grained ontology of research topics in computer science. And it's more comprehensive than alternative solutions, even the topics that are within OpenAlex. Just to give you a comparison, OpenAlex has got at the moment 4,500 topics in all science. Here, only in computer science, we have 14,000 topics. You can imagine the level of depth that we are able to achieve with this. To do so, I mentioned, we take title and abstract, then we have 3 modules inside the classifier. We have a syntactic module that extracts pieces of topics that are explicitly mentioned. You know, for example, in the abstract, you find the keyword neural network. That's a topic. Then there is a semantic module that uses embeddings, and Yuan has done a great job to tell us what embeddings are. Therefore, it saves me time to do so. But in general, what we do is to infer words that are not explicit but are implicitly available. For example, there is a piece of text that, thanks to the word embedding, to similarity matching, it is able to trigger one of the CSO topics. And then we do some post-processing to clean up a bit the topics and to infer others that are ontologically similar. So this is pretty much it. So at the end of this exercise, we have papers that have been annotated with topics. And as I mentioned, these topics do not stop only at the disciplinary level. They go very deep in the hierarchy, that we can somehow associate them as expertise level of authors. So data selection. We selected 114,000 papers fulfilling some constraints that were published between 2010 and 2015. This is simply because we wanted to have one time frame, and all the papers, the characteristics of all the papers were contained within the same time frame. Then at least 2 citations, just to avoid like papers that perhaps are editorial notes or things that are not really research paper. This allows, it's just a quality check. Papers that have been authored by at least 2 authors. This is a kind of constraint to determine that there is a team there. Otherwise, if it is a paper authored by one author, there is no team there. And of course, the last constraint is that at least each author needs to have a prior publication. Otherwise, it's impossible to determine their expertise. Those are the kind of constraints. So we selected 114 papers, and we organize them in different buckets according to their citation that they've been gathering after 5 years, right? This is important because within each group, given all the papers, within each group we will later, as I will show you, we are going to map their average in diversity index to see whether there is any difference according to the different ranges of citations. Cool. So to determine the author expertise, we characterize the. Sorry, I just got lost for a second. So we extracted the papers in the 5 years prior prior the time of collaboration, and we computed the distribution of the topics for each author, and then we identified the top most relevant topics for each author. So imagine you have a paper. You have different authors, and for each author, you have a selection of the top 10 topics that were extracted for each author. That will determine their expertise. So out of 114,000 papers, we processed 363,000 authors, and as a result, each author is now associated with a distribution of their top most 10 relevant topics. To assess diversity of expertise within the paper, we use 2 statistical metrics. The first one is the maximum value, in which of all the pairwise cosine distances, and the number of subteams. I will explain those 2 in more detail. So for the maximum value, so imagine within each paper, within all the authors, we take each pair of authors, and then we compute the cosine similarity to understand exactly how these distributions are equal to each other. Are they equal? Are they different? So after this computation, we get a distribution of cosine similarities, and we get the maximum value. So this means that the higher is the cosine distance, the more diverse is the set of topics between each 2 authors. We could have used other indicators, such as the average, for example, but we identified that the average is actually not really a good indicator, because, for example, imagine you have 2 authors, one in artificial intelligence and one in human-computer interaction. Of course, these 2 authors seemingly are different in their expertise, right? But then, so there is high diversity. But then, if you put, for example, 3 authors in artificial intelligence and 3 authors in human-computer interaction, their average diversity will be lower, although we all know that the team is very diverse. That's why in this case we use the maximum value, and it helps us identifying whether at least there is one person that is different from the crowd within the team. The other one is assessing the number of subteams. The number of subteams. And for doing this, what we did is, again, we computed the pairwise cosine similarity between each couple of authors, and we understood exactly which authors are most similar to each other. Are there subgroups? Are there organic subgroups of people in the team, right? This is an example. You can see there are 3 authors which share kind of the same topics. 3 authors. There is one author that is isolated, and there are other 3 authors that have got another different distribution of topics. And based on the number of these subgroups, we are able to tell whether the team is very diverse or perhaps is not diverse at all. So we have classified the number of subgroups that we are able to extract for each paper, whether its diversity is low, moderate, high, and very high, according to the number of components. We call them components because in network science they're called connected components. But based on the number, we identify what is the sort of class of diversity that is available in the paper. So now it's to investigate the relationship between diversity and expertise, diversity of expertise and citations, we use 2 metrics. And we compared the indices of diversity that we extracted in each bucket according to the chi-square test and the Pearson correlation coefficient against the citation median. Okay, those are the results. This is just for the maximum cosine distance, so the first indicator that I talked to you about. And what you can see is that these are the distribution of maximum values in all the buckets. Okay, so there are 10 buckets of citations, and these are the maximum distributions. So, for example, what you can see here is that, just to recap a little bit, 1 means that there is at least one author in the team that is diverse from the others, right? So it means that now I don't remember the number, but for papers that have got citation above 150 after 5 years, there are more than 2,000 papers which are highly diverse. Okay, there are authors that are diverse. So one interesting finding here is that the distributions between 0.1 and 0.9 are kind of the same. You can see they are very similar, at least in shape, right? But what is different instead is the values of 0, which means that all the authors are similar, they have all the same expertise, so the team is very coherent in expertise, and in 1, where there is at least one author that is different from the others. Okay, so we put those in comparison within a table, and what we realized actually is that their ratio, the number of 1s and the number of 0s for each bucket of citation, is actually correlated with the number of citations. So the higher the citation goes, the higher is the ratio between the number of 1s and the number of 0s that I showed you here. Okay, so the Pearson correlation coefficient is 0.95. This suggests that the higher expertise diversity leads to, potentially leads to higher number of citations. With regards to the same, with the number of subteams, we have done the same exercise. So according to the number of citations, we report the percentage of papers, okay, that have got low, moderate, high, and very high. Just to remind you, those are with 1 and 2, a number of subteams, 3 and 4 subteams, 5 and 6, and beyond 7 subteams, right? So what we can see is that the number of papers with low diversity, it's inversely correlated with the number of citation, okay? So the higher the citations, the percentage of number of subteams becomes lower. And instead, the percentage of paper with high diversity is positively correlated with the number of citations. And also here we create the ratio between very high plus high against low, and what we can see is that the Pearson correlation coefficient is around 0.9, highlighting the fact that like a highly diverse team effectively leads to a higher number of citations. To conclude, yes, we investigated whether diversity of expertise in a research team can influence the scientific impact, of course, the scientific impact of a paper, and which is measured in terms of number of citations received by their papers in the upcoming 5 years. And what happens is that in this study that includes 114 papers in computer science, we have that it is like that. So it affects, it influences the number of citations. Moving forward, we are planning to study other disciplines like material science, engineering, and medicine. Also analyzing diversity of teams in academic institution and industry, whether collaboration between these two can lead to an increased impact, and also try to do more multidimensional analysis, including other features that I mentioned to you at the beginning, so to not have only one feature of analysis. Yes, that's almost all that I have to say. Thank you.